trillion of value is left on the table because it's difficult to collaborate, especially on sensitive data. So privacy-sensitive data, confidential information, antitrust information. And the reason for that is that it's especially complex from a legal perspective, which makes it technical, complex, and therefore it's costly, very time-consuming. And we believe we can remove this largest barrier by protecting data privacy. And data privacy is actually, it's a strange word because it's actually not existing. Privacy is about people, it's about individuals. If you look at, for instance, GDPR, privacy tells you that if you break the privacy, you invade somebody's personal atmosphere, somebody's personal living. It jeopardizes somebody's security. And to illustrate that with a little example, how that can work. Because yesterday we talked a lot about securing data privacy by running computations on encrypted data, which is a fantastic way of providing data protection. But privacy is also about keeping control, especially if you want to collaborate with multiple parties. It's essential that you as a data owner can remain in control of what's being done with your data. So if we would illustrate that with a simple example in the room, then what we could do using privacy technology is I could ask you to share your income, and we could compute the average salary of us in the room without learning any of your salaries. That's a very simple thing that we could do. Once I've done that, I can ask Christina to leave the room, and I can run the same computation again, and then we learn Christina's salary. That's very simple. So we can provide excellent privacy guarantees about the input data, but the output actually reveals very sensitive information. So it's essential that you get a grip on that. And that's actually what we did in the product that we've built. Virtual Data Lake is a product that enables organizations to collaborate on their sensitive data without sharing it. You can run computations on encrypted data, but you can also have very strict purpose binding, so you can remain in control of what's being done with your data. And the fundamental technology behind it is multi-party computation. It's a cryptographic technique. And what I wanted to explain a little bit, because yesterday a lot of people asked the question, how can you run computations on encrypted data? For multi-party computation, I thought it would be nice to give you a little bit an understanding about the math behind it, and then illustrate that with a use case of how our technology is being used by a law enforcement agency. So if you want to connect data, basically you're trying to connect tables, right? So I have 3 parties over here. They all have information about individuals, people. And it's, let's pretend that this is very sensitive information. That's the date of birth, for instance, or somebody's weight. And we want to connect those tables. So we basically want to create one single table that holds the individuals that are appearing in all those tables, so we can connect this data. In order, for instance, if we want to compute what the average age is of somebody with a certain length. I don't know, it's a stupid relationship, but if you want to compute that, you can compute that by connecting these tables. So how does that work if you would do that in a multi-party computation setting? I again have the same tables, but I encrypt them. So they're moved to the blind. And in this encryption technique, I also start to chop them up. So every piece of data is split in multiple random numbers. And I can spread those random numbers in a network of computers. And the funny thing is that this network of computers, none of the computers hold the full information. They all contain random noise. But I can compute on these different servers. I can run computations as if it is the same table that we created before. So I can do exactly the same computations, but this full data table is not apparent anywhere. It's not existing. It's an iteration over the internet between the computers. Does it make sense, or is that still too much magic? I don't know. I want to get out of the magic because it's actually math. It's just mathematics. So the technology that we use is the basics is called secret sharing, and how that works is you take a number and you split it in multiple puzzle pieces. And we do that in such a manner that every piece of the puzzle behaves like random noise, but we're going to agree in this room a secret, and this secret is the relationship between those puzzle pieces. So for this simple example, we agree that the relationship between our puzzle pieces is that we compute with clock arithmetic. That's difficult for me in English to pronounce, but so every number is a multiplication of the number of 12. So 9 is 9, but 21 is also 9. And 14 is 2, just like you use in normal clock arithmetic. So if I take the number 7, I can split that in a random number 3. I can choose another random number, 8, but the last number, that's determined by the secret. So the last number is also 8. So then the total of the numbers is 19. Does that make sense, or am I going too fast? So basically this last number is there because we agreed that the secret is there, that it's also always... so I have a secret, and now we can, since every number is a random number, we basically, if we send this number to a computer, this computer only holds this randomness. I can mathematically prove that the 3 does not reveal anything about the 7. Do you agree or not? Because if we think that that's not true, then then the whole... so this is what we call the shares, the secret shares. And now the funny thing is that, can you run computations on secret shares? So on random noise. We just agreed that this is random noise. So I take another number that we split. We have the number 2. I split it in the number 11. 1 and then 2. So that's 14 combined. And we agreed that 14 is actually 2. So if I start to add those numbers, you actually see that the random 3 with the random 11 holds again a 2, because this is 14 and then I have a 2. Same over here. 8 and 1 is 9. 8 and 2 is 10. And if I add those numbers, I get 21, which is 9, which is actually the same as I had over here. So this is the simplest way of running computations on random noise. The thing is, if you do this, if you make a multiplication, it is already 100 times more complex than the simple example. So that's where the difficulty is. If you want to, so additions are quite simple, but as soon as you want to run more complex computations, the problem, the complexity increases like exponentially. So that is the challenge that we face when we want to create these new technologies to keep the overhead low. So does it make sense? Do you have the feeling that it is possible that we can run these type of computations? Because in reality, of course, the secret is not as simple as this clock arithmetic. It's much more complex cryptographic protocol. So how do we use this in practice? And I was looking through the use cases, and what is interesting to share. This use case is not about GDPR. It's about sensitive data in the form of confidential information. So we have a law enforcement agency, and in this use case, it's a human trafficking use case. So Romanian women working in the sex industry are being trafficked to the Netherlands. And we have multiple parties in this respect. We have the police. It's actually trying to uncover trafficking networks. And we have NGOs. Those are 8 organizations that are actually active in cities in the Netherlands in supporting women to provide security or healthcare, all kinds of different forms of aid. And they have actually people working from them in the fields that provide sensitive information about these networks. For instance, in Romania, these women provide information how they are recruited. So if you know how they are recruited, you can prevent this recruiting taking place. So for instance, this takes place in high schools. So when they discover how this takes place, they actually try to take measures to prevent that. These women it's very sensitive information what those women are sharing, and especially the fact that those women are doing that. Those women are working for pimps, and as soon as people find out that they are actually sharing information with others, they disappear directly to another city. And what the police wants to do is they want to follow certain individuals, so have a list of victims and suspects. And they want to uncover those networks by shadowing, by following people in the field. But what you want to avoid is that as soon as the police starts to follow an individual, that is actually also an informant for the healthcare organizations. That is something that you don't want, because then directly this individual is basically disappearing. So what we want to do is we want to compare those lists of informants and suspects. And you can all imagine that the police is not able to share all the people that are on their list and that they suspect to be part of such a network. And you can also imagine that the NGOs are not able to share the information on their list. So in practice, you cannot share this information. And you need this information to protect these women. And using multi-party computation, we are able to make the comparison between those lists in the blind. So what we did, the example that I showed of merging the tables, here we actually subtract the tables from each other. So what we do is, we look at the individuals on that list in the blind, we look on the individuals on this list, and we see where the overlap is. And as soon as we see overlap, we subtract those individuals, and the remaining list, there we take a sample, and we say to the police, okay, these people, if you start to, they wanted to follow 10 people, we made a selection of 10 people that are basically whitelisted. The only thing is that if police officers, if they write down the name of a Romanian woman in the Netherlands, you can imagine that those names are spelled wrongly. So we built a simple machine learning algorithm that we trained on public data that is able to cope with those spelling errors. So you can not only match directly, but you can also do a fuzzy matching between the list. And then you take so for example, if you have the name Freya, which is my colleague, actually, her name is often spelled wrongly, but now we find the same Freya. So we can make sure that if we have this discrepancy between the list, that we still make sure that we remove this name from the list and not that by any accident she is involved. So using this same technology, we apply it in many other use cases. Like cyber threat intelligence, there we do it to share sensitive cyber attack information for the National Cybersecurity Center in the Netherlands. For electricity, for a big electricity grid operator, we use it to run analysis on smart meter data. So it's very sensitive data because the data in your house actually reveals a lot about who's in the house and what you're watching on television, for instance. But most of the cases are actually in healthcare. So looking at real-world evidence, so treatments, how if you make changes in the way that medicine are prescribed, what's the effect of that in the real world. Also showing the effectiveness of preventive treatments, which is quite difficult to prove, but you can prove it because you can follow a patient across many different healthcare providers. So it's all very impactful use cases. And I think that's the biggest driver for these kind of technologies, that in the future, I expect that these type of technologies will become much more user-friendly. Like Rand was sharing yesterday, with homomorphic encryption, it will go really fast. There will be many different type of use cases or applications where you can use these powerful technologies for. And I think we only at the beginning of extracting real value from data. There's so much more value that we can extract. So really looking forward to how this evolves. And thank you very much for your attention, and hopefully this was interesting for you.